Good evening, students. Welcome in next lecture of Math F242 Operation Research. Audio is okay. Okay, thanks. So in morning we have covered the MM1 FCFS M infinity, infinity and infinity. That is the single server model. Now next model is MM1 FCFS M infinity. So what is the meaning of this? It shows that we have the infinite population. Infinite population. Here we have the finite population. Finite population and population size is M. So, or not finite population, finite capacity. Finite capacity. So here the capacity size is the M. Means at most M customers can be accommodated in the system. So when we say the finite capacity, it means it is the capacity of the queue plus in service. When we talk about the capacity, it means we are talking about the queue plus in service. Then this is the service discipline. Service discipline. So here we have the standard service discipline, that is the FCFS, first come first serve. Then we have the number of server, that is the single server model. Here it shows this M, the service time follow the exponential distribution with parameter mu. That implies that the current model is the Markovian model or Poisson cube. And here we have the inter-arrival time also follow the exponential distribution with parameter lambda. Or sometimes we can have the arrival follow the Poisson process. So both will be the same thing. Either we say the arrival follow the Poisson process or inter-arrival follow the exponential distribution. So it that we represent as a Markovian property or memoryless property or Markov property. That's why we represent it by the M. So MM1 FCFS M infinity. This is the single server finite capacity queuing model. Right? It is the single server finite capacity queuing model. So in this case, what can be the situation due to the single server? We have the, or due to the finite capacity and single server, we have the state dependent rate lambda n as a lambda for I is equal to 0, 1, 2, and m minus 1, and it is 0 uh, for n is equal to, and for n is equal to m, m plus 1, m plus 2, and so on. It is 0, and mu n will be mu n, since it is a single server model, so it is mu for n is equal to 1, 2, 3, and so on. So here we have the state dependent rate. So if you make the state transition diagram, initially we have the 0 customer, then 1 customer, then 2 customer, right? 3 customers. We know that we represent the node, right? We represent node, right, for the state of the system. Then here we have the n minus 1 customer, n customer, n plus 1 customer. Then after we have the m minus 1 customer and m customer, because at most m customer can be accommodated in the system due to the finite capacity, because the capacity size is m. So more than m customers we cannot accommodate in the system. It is given to you lambda naught is equal to lambda 1 is equal to also lambda 2 is also lambda, and lambda n minus 1 is also lambda, lambda n is also lambda, and lambda m minus 1 is also lambda. Afterward, because of the finite capacity, there is no possibility of joining of a customer. We assume that lambda is equal to 0, right? So that's why here it is written lambda is equal to 0. Now service, we have the single server, so service rate will be the mu. Here the service rate will be the mu, here service rate will be the mu, and here service rate is mu, and here the service rate is mu. Now if you want to write the Chapman-Kolmogorov differential difference equation, Chapman-Kolmogorov differential difference equation. So how we can write? If you want to write for the zeroth node, so this will become dp0t by dt, outgoing with the negative sign, minus lambda p0t, incoming with the positive sign, so mu p1t, mu p1t. For the general node, if you want to write dpn t by dt, so outgoing will be the minus lambda plus mu pnt plus incoming lambda n minus 1, or lambda, because all the lambdas are the lambda, so lambda pn minus 1 t plus mu pn plus 1 t. For the general node, this is the outgoing, this is the outgoing, here we have the incoming, here we have the incoming, so that will come with the positive sign. Now here the n vary from 1 to m minus 1. Now we have to write for the mth node, so here d pmt by dt will become minus mu pmt plus lambda p m minus 1 t, with initial condition p0 at t is equal to 0 is equal to 1, and pn 0 is equal to 0 for n is equal to 1 to up to m. So under this initial condition, this is the initial value problem, right? We have to solve the following system of first order first degree differential difference equation. Then after we write the steady state equation. So steady state equation will be, when we take the t tends to infinity, right? So d by dt will be become 0. So this will become lambda p0 plus mu p1 is equal to 0 minus lambda plus mu pn plus lambda pn minus 1 plus mu pn plus 1 is equal to 0 for n is equal to 1 to m minus 1, and minus mu pm plus lambda pm minus 1 is equal to 0. With normalizing condition, in general, normalizing condition is what? Sum of all probability is equal to 1, means n is equal to 0 to infinity, pn is equal to 1. But here we have the pm plus 1, pm plus 2, pm, all are the 0. So this can be reduced, this can be written as n is equal to 0 to m, pn is equal to 1. So here we have the modified normalizing condition for this. So now we solve the following system of linear equation for computing the all the steady state probabilities. So we have the two ways to solve. Either you solve the following system of equation using the using product type solution, or we know how to write, how we have already solved the worth and death process. So from there we are computing the steady state probabilities. So we know that what is the pn? Pn is equal to c naught into p naught. where Cn is what, right? Approach is exactly same. So Cn is what, lambda naught, lambda 1, lambda n minus 1 upon mu 1, mu 2, mu n. And we know that all the lambdas, are lambda. So lambda, 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 and here we have the mu, mu, and mu, which can be written as lambda upon mu power n, or you can say rho to power n. So this will become rho to power n p naught for n is equal to, 1, 2, and here we have the m. And Cn means this is true for the n between 1 to m, and this is equal to 0, right? Or you can say this is equal to lambda, 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 then 0, 0, and 0 upon mu, mu, and mu, 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 and mu. So this will become 0 for n greater than equal to m plus 1, right? Because after m, we know that here the state arrival rate is given to you as a 0. So when we include, the Cn will become the 0 for the n greater than equal to m plus 1, right? Up to the m, it will be the rho to power n. So this will become 0 for n is equal to m plus 1, m plus 2, and so on. Up to the m, right? Up to m, we have rho to power n p naught. Now p naught is unknown here. So by normalizing condition, what is the normalizing condition? Here the normalizing condition is summation n is equal to 0 to infinity pn is equal to 1. And for this case, we know that because pn is equal to 0, for m plus 1, m plus 2, right, and so on. So this will become summation n is equal to 0 to m pn is equal to 1. That is p naught, p1, p2 plus pm. And other than this, all are the 0. So p1 is what? If you take the p naught common, so 1, p1 is what? Rho into p naught, that is the rho. P2 is what? Rho square into p naught. P naught you have taken common, so rho square. And what is the pm? It will become the rho to power m into p naught. Rho to power m into p naught. So what is this? This is the geometric series with with first term 1, common ratio rho, and last term rho to power m. This is the finite geometric series, right? This is the finite geometric series. So its sum will be p naught, its sum will be the 1 minus rho to power m plus 1 upon 1 minus rho. Clear? Is there any doubt? So from here, the p naught will come 1 minus rho upon 1 minus rho to power m plus 1. Why we are using this? Because rho is less than 1. Why the rho is less than 1? Lambda upon mu less than 1, or lambda less than mu. So we assume that effective for solving any queuing system, always the arrival should be lesser than the service, right? So that then only you can solve the equation, otherwise there is no explosion of the q. So when we have this p naught, so pn will become 1 minus rho into rho to power n upon 1 minus rho to power m plus 1, m plus 1. And here we have the, here n is equal to 1 2 up to m, and it is 0 for n is equal to m plus 1, m plus 2, and so on. So that's we have computed the pn. Now in this case we have assumed that rho is less than 1. Then we have this result. If if rho is equal to 1, that is lambda is equal to mu. If lambda is equal to mu, then what will be the pn? So when we put rho is equal to 1 in this equation, if you put rho is equal to 1 in above equation, we will get what? 0 upon 0 form. So that we cannot solve, right? 0 upon 0 form we have, so that we cannot solve. So in this case, if lambda is equal to m, at that time what is the cn? What is the basic formula? Lambda naught lambda 1 lambda n minus 1 upon mu 1 mu 2 mu 1. I am saying that lambda is equal to mu, so this will become lambda lambda lambda. In general we have the lambda lambda lambda, right? Mu and mu. So when the lambda is equal to mu, so it will cancel out, so that is equal to 1. Cn is equal to 1 for n is equal to 1 2 up to m minus 1. And we know that pn is what? Cn into p naught. Cn into p naught, that is the p naught for n is equal to 1 2 and m. So that is your pn. Pn is equal to p naught. And by normalizing condition, what we have? We have the sum of pn for n is equal to 0 to m is equal to 1. That is the p naught plus p1 plus p2 plus pm. And we know that all the pn is equal to p naught. So here we have the p naught common. So here we have the 1 plus 1 plus 1. How many times we have the 1? How many times we have 1? So p naught into m plus 1. We have the m plus 1 times once, right? So here we have the m plus 1. So p naught will come 1 upon m plus 1. If the lambda is equal to mu, at that time p naught is equal to 1, 1 upon m plus 1, and pn is what? Pn is given to you, pn we have computed as a p naught. So pn will also be the 1 upon m plus 1 for n is equal to 1 2 up to m. So that is your pn. So we have computed the state probabilities pn when lambda is not equal to mu and when lambda is equal to mu. So now we can write pn is equal to what? It is the 1 minus rho to power n upon 1 minus rho to power m plus 1. It when n is equal to 1 to m, 1 to m, or that 0 will also work. 0 will also work here. So 0 1 to m and lambda not equal to mu. It is 1 upon m plus 1 for n is equal to 0, 1, 2, m, and lambda is equal to mu, and it is 0, right, elsewhere. It is 0 elsewhere. So this is your state probabilities. After having the state probabilities, because state probabilities are important thing, so from the knowledge of the state probabilities, we can compute the other system performance. System performance means LQ WQ, means all the expected value we can compute easily. Anything you want to ask up till here? Any derivation if you are not able to understand? So now system performance. So in this case, first, what is the L? Expected number of customers in the system. Expected number of customer in the system. So we represent it as a En, and En is what? Summation n into Pn for n is equal to 0 to infinity. But for this, due to the finite capacity, we know that Pm plus 1, Pm plus 2 is equal to 0. So this will become n is equal to 0 to m, n is equal to 0 to m, and n Pn. And due to the n is equal to 0, the sum will be the 0. So here we can say that n is equal to 1 to m n Pn, npn. So this will become 1p1, 2p2, 3p3, and here we have the mpm. Clear? mpm. And already we have computed the value of the all the pns. So what the value of the pns? It is the p naught, right? Rho to power n into p naught, and p naught is what? P naught is 1 minus rho upon 1 minus rho to power m plus 1. That is p naught. So inside we have what? Rho 2 rho square, 3 rho cube, and plus m rho to power m. That is your p1, p2, p3, right? Pm. Clear? So let's say this is the s is equal to rho plus 2 rho square plus 3 rho cube plus m minus 1 rho to power m minus 1 plus m rho to power m. This is your s. If you multiply by the rho on both sides, we have the rho square plus 2 rho cube, 3 rho to power 4, m minus 1 rho to power m plus m rho to power m plus 1. Clear? If you do the first minus second, 1 minus rho into s. So rho 2 rho square minus rho square, 3 rho cube minus 2 rho cube. Similarly, m rho to power m minus 1 rho to power m, then minus m rho to power m rho to power m plus 1. So what is the sum of this? This is the finite geometric series with the first term rho and common ratio rho. So its sum will be rho 1 minus rho to power m upon 1 minus rho minus m rho to power m plus 1. That is the finite geometric series, and we know that rho is less than 1. So S will be rho 1 minus rho to power m upon 1 minus rho whole square minus m rho to power m plus 1 upon 1 minus rho. That is the required sum. So when we put this required sum here, so what is the P naught? P naught is 1 minus rho upon 1 minus rho to power m plus 1. And what is the S? S is the rho 1 minus rho to power m upon 1 minus rho whole square minus m rho to power m plus 1 upon 1 minus rho. That is your L. If you solve it, so here we have the 1 minus rho upon 1 minus rho to power m plus 1. So here if you take the LCM, 1 minus rho whole square, and here we have the rho minus rho to power m plus 1 minus 1 minus rho, if you multiply here minus, so this will become m rho to power m plus 1, and minus minus plus plus, here we have the m rho to power m plus 2, m plus 2. So 1 minus rho and 1 minus rho, here we have the cancellation. Now so this can be written as, if you add the like term, so rho minus m plus 1 rho to power m plus 1, right? If you combine the second and first term, plus m rho to power m plus 2 upon 1 minus rho 1 minus rho to power m plus 1. This can be written as rho minus rho to power m plus 2 minus m plus 1 rho to power m plus 1 plus m plus 1 rho to power m plus 2 upon 1 minus rho 1 minus rho to power m plus 1. Means we add and subtract by the rho to power m plus 2. We add and subtract with rho to power m plus 2. So from the first two term, if you take the rho common, 1 minus rho to power m plus 1. And from the second two terms, if you take the common m plus 1 row to power m plus 1, so inside we have the 1 minus row, 1 minus row, and here we have the 1 minus row, 1 minus row to power m plus 1. Here we have the 1 minus row, 1 minus row to power m plus 1. So 1 minus row to power m plus 1, 1 minus row to power m plus 1. If you cancel out, so here we have the row upon 1 minus row minus 1 minus row and 1 minus row. If you cancel out, so here we have the m plus 1 row to power m plus 1 upon 1 minus row to power m plus 1. So this is the this is the L, right? L, and this L we compute when rho is not equal to 1 or lambda is not equal to mu. Using those formula, those values of the Pn, we have computed this L. Now we have the, for this model we have this one special case when lambda is equal to mu or rho is equal to 1. At that time we know that Pn is equal to 1 upon m plus 1. What is the L? L is the summation n into Pn, n is equal to 0 to m. That is the P0, P1, n into P1. So it is the 0 P0, 1 P1, 2 P2 plus m Pm, m Pm. So this will become, if you take the, because P1, P2, P1, P2, Pm all are the 1 upon m plus 1. So 1 upon m plus 1 you write outside, and here we have the 1 plus 2 plus m, and it is what? It is the sum of the natural number. So this is equal to 1 upon m plus 1 m into m plus 1 upon 2. So this m plus 1 and m plus 1 is cancelled out. So here we have the m by 2. So on an average, the whatever the capacity size, right, half is filled with the customer. If lambda is equal to mu, at that time expected number of customer in the system is m by 2. So in this way we can compute the expected number of customer in the system for the single server, right, for the single server finite capacity model. Clear? Now if you have to compute the lambda var is what? Lambda var is, what is the lambda var? Summation n is equal to 0 to infinity lambda n into Pn. This is the general formula, but we have seen lambda m plus 1, lambda m plus 2 all are 0. So this will become summation n is equal to 0 to m minus 1, 0 to m minus 1 lambda n Pn is equal to 0. That can be written as summation n is equal to 0 to m minus 1, all the lambdas. In starting we have seen all the lambdas are lambda. If you see here, we have written all the lambdas are lambda, right, up to the m minus 1, and it is 0 from m plus 1, m plus 2. So, so here we write the lambda into Pn, which can be written as lambda summation n is equal to 0 to m minus 1 into Pn. Can anyone tell what is the value of this summation? Yes, it is the 1 minus Pm. So lambda into 1 minus Pm. So that is our lambda bar. So lambda bar is equal to, means effective lambda bar, effective arrival rate is equal to lambda into 1 minus Pm. Means there are some lost customer, means there are some customer who is not able to take the service, who is not able to join the system. So that is the lost customer. Due to the lost customer, we have the loss of the revenue. That's why we have the this is the important one. So here the lambda bar is equal to lambda into 1 minus Pm. So this is true when rho is not equal to 1. If this is the lambda bar, lambda and 1 minus Pm is equal to 1 upon 1 m plus 1 in case of rho is equal to 1 or lambda is equal to mu. At that time, just you put the value of the m. So here we have the lambda, right? So m plus 1, m plus 1 minus 1. So this will cancel out. So here we have the m lambda upon m plus 1 when we have the rho is equal to 1 or lambda is equal to mu. At that time, lambda bar is equal to this. Clear? That you have to remember. For the special case, you have to remember what is the value of the lambda bar. Now, if you compute the LQ, what is the basic formula of the LQ? LQ is the EQ. EQ, that is the expected number of customers in the queue. Expected number of customers in the queue. So here we have the summation. Basic formula is what? N minus S into Pn. N is equal to 0 to infinity. But we know that P m plus 1, P m plus 2 and so on are 0. So this will become N is equal to S. This is from the S. So N is equal to S to M. N minus S into Pn. N minus S into Pn will be the required formula. So which can be written as
npm minus spm.
actually I want to correlate it with the L.
So here s will be 1, so we can do it using that.
Okay. S is equal to 1 we have. So it will become summation N is equal to S to M, S to M or 1 to M. Okay. 1 to M N Pn NPN minus summation Pn for N is equal to 1 to M. Clear? That we have written. S is equal to 1. So N is equal to 1 to M. So what is the first summation? First summation is, yes, L. First summation is L. And what is the second summation? Second summation is P1 plus P2 plus PM. So second summation can be written as L minus 1 minus P naught, right? But from this formula, L minus 1 minus P naught, so from this formula, we are not able to judge whether it is the finite capacity model or not. So we try to write in the different form. So here we know that what is the Pn? What is the Pn? Pn is equal to Cn P naught. What is the Pn plus 1? That is the Cn plus 1 P naught. If you take the ratio, both are true when n is less than equal to m. When we have the n is less than m, when n is less than m, then Pn is equal to Cn P naught, and Pn plus 1 is equal to Cn plus P naught. So when we take the ratio, P naught and P naught cancel out. What is the Cn? What is the Cn? Lambda naught, lambda 1, lambda n minus 1 upon mu 1, mu 2, mu 1 upon what is the Cn plus 1? Lambda naught, lambda 1, lambda n minus 1, lambda n. What is the upon mu 1, mu 2, mu n plus 1. So we have the cancellation of these terms. So we have the very important formula here. Pn upon Pn plus 1 is equal to Pn upon Pn plus is equal to mu n plus 1 upon lambda n. Clear? Or Pn plus 1 is equal to lambda n upon mu n plus 1 into Pn. That is the important relation for n from 1 to m. Now, in this case, what is the lambdas for this range of the n? What is the lambda? All the lambdas are lambda. All the mu's are mu. Pn. So this will become rho Pn. Pn plus 1 is equal to rho Pn. So using this theory, this can be written as L minus. Now in the bracket, what we have? P1 can be written as rho P naught. P2 can be written as rho P1. And last we have the PM. PM can be written as rho PM minus 1. So if you take the rho common, inside we have the P naught, P1 and PM minus 1, which can be written as L rho 1 minus PM. So that formula we use LQ is equal to rho LQ is equal to L minus rho 1 minus PM. So from here we can say that it is of the finite capacity model, because in this we have the variable m. So this formula generally we use. Our formula is also right, but in general we use this formula. So this formula is true when rho is not equal to 1 or lambda is not equal to mu. If we have the lambda is equal to mu or rho is equal to 1, so LQ will be what is the L at that time? L is equal to m by 2. minus rho is equal to 1, rho is equal to 1, 1 minus Pm is equal to 1 upon m plus 1, m plus 1. So this will become m by 2 minus m by 2 minus m upon m plus 1, m plus 1 minus 1. So yes, m upon m plus 1. So if you want to write, you can write the LCM 2 m plus 1. So we have the m square plus m minus 2m. So this can be written as m square minus m upon 2 m plus 1. So that can be written as m into m minus 1 upon 2 m plus 1 for rho is equal to 1 or lambda is equal to mu. So in this way, we can determine the value of the L and LQ. Lambda bar already we have computed, right? Lambda bar already we have computed here. So from the lambda bar, right? This we have already computed lambda bar as a lambda into 1 minus Pm. So from the knowledge of the lambda and L, using the little formula, we can compute the expected waiting time. So what is the W? W is E of t, that is the expected waiting time. Expected waiting time of the customer in the system and by the little formula, it is the L upon lambda bar. So L we have computed as a rho upon 1 minus rho. So this will become L upon lambda 1 minus Pm, and it will be the rho 1 minus rho minus m plus 1 rho to power m plus 1 m plus 1 rho to power m plus 1 upon 1 minus rho to power m plus 1 1 minus rho to power m plus 1 into 1 upon lambda 1 minus Pm. So this can be written as rho 1 minus rho minus m plus 1 rho to power m plus 1 upon 1 minus rho to power m plus 1 into 1 upon lambda 1 minus. What is the Pm? It is the rho to power m 1 minus rho to rho upon what is the P naught? 1 minus rho to power m plus 1. That is the value of the Pm. So when we solve this, so it is the 1 upon lambda rho upon 1 minus rho minus m plus 1 rho to power m plus 1 upon 1 minus rho to power m plus 1. Just I will take the 2-3 minutes more. So it will be the 1 minus rho to power m plus 1 upon 1 minus rho to power m plus 1 minus rho to power m minus minus plus rho to power m plus 1. So rho to power m plus 1 and rho to power m plus 1 is cancelled out. So in the denominator we have the 1 minus rho to power m. So we have to write it in the with some good form. So if you write it, so here we have the 1 upon lambda, and here we have the rho into 1 minus rho to power m plus 1 upon 1 minus rho into 1 minus rho to power m minus m plus 1 rho to power m plus 1 into 1 minus rho to power m plus 1 upon 1 minus rho to power m plus 1 1 minus 1 minus rho to power m 1 minus rho to power m. Now from the numerator you can see we can take rho common, and rho is equal to what? Rho is equal to 1 upon lambda, lambda upon mu. So if you take the rho common and you write as a lambda upon mu, and you cancel this lambda, so here we have the 1 upon mu. I am saying that take rho common, take rho common and cancel cancel lambda, so we have the 1 upon mu, 1 upon mu. So this rho you have taken common, 1 minus rho to power m plus 1 upon 1 minus rho, 1 minus rho to power m minus, here we have taken the rho common, so here we have the m plus 1 rho to power m, 1 minus rho to power m plus 1 upon 1 minus rho to power m plus 1, 1 minus rho to power m. So 1 minus rho to power m plus 1, 1 minus rho to power m plus 1 is cancelled out here.
Sir,
Yes,
sir, why did mu come in the denominator instead of lambda?
actually I have said na, we take the rho common, we take the rho common,
Okay, then, oh, right, yes, sir.
and rho is equal to lambda upon mu.
Yes,
That
sir.
that lambda is cancelled out. That I have written here na.
Yes, sir. Okay, okay. Yes, sir. Got it.
So it will become the, which can be written as 1 upon mu rho into 1 minus rho to power m upon 1 minus rho into 1 minus rho to power m plus 1 minus rho, 1 minus rho, so that this rho and rho cancel out, minus rho to power m upon rho to power m upon 1 minus rho to power m minus m rho to power m upon 1 minus rho to power m. Right? So we have separated the all the things. So the benefit of this, if you write in the separate fraction, so the benefit of this is just last line 1 upon mu. This can be written as rho 1 minus rho to power m upon 1 minus rho to power m. So this will cancel out. Plus 1 minus rho upon 1 minus rho to power m. So here this is cancel out. Minus rho to power m upon 1 minus rho to power m minus m rho to power m upon 1 minus rho to power m. So after cancelling this, we have the 1 upon mu. From the first one, we have the rho 1 minus rho. From the second and third one, we have the plus 1. From the second and third one, we have the plus 1 minus rho to power m upon 1 minus rho to power m. And here we have the m rho to power m upon 1 minus rho to power m. 1 minus rho to power m. So which can be written as, if you combine the first and second, so last 1 upon mu, this can be written as 1 upon 1 minus rho minus m rho to power m upon 1 minus rho to power m. So this formula now you have to use for writing the LQ. So this is the W, not LQ. This is the expression for the W. When rho is not equal to 1 or lambda is not equal to mu. Anything you want to re-explain? And when lambda is equal to mu, directly you know what is the formula. So when lambda is equal to mu, at that time L is equal to what? L is equal to m by 2, right? Lambda 1 minus 1 upon m plus 1. So whatever the solution will come, accordingly you write. So that is the value of the W in case of the, right? So it will become m by 2 upon lambda m upon m plus 1. So m and m cancel out. So this will become m plus 1 upon 2 lambda. So that is the W in case of the rho is equal to 1. Clear? So rest we will do in next class. Tomorrow we will do then numerical example on these 3 models. We have covered till now the 3 models. So tomorrow we will cover the 3 models.
Thank you, sir.
Okay.